Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 36, and it is entitled Light and Characteristics of Sound. I want to focus in this lesson mostly on sound. We spent a good deal of time with light in Lesson 29. So if you're looking for light, I'm going to refer you back to 29. We're going to see that sound is a longitudinal wave. You'll remember the difference between transverse and longitudinal waves. Sound is one of the longitudinal waves that we're going to study. Any kind of pressure wave is a longitudinal wave. It is a mechanical wave, and it requires a medium to travel in. I want to show a couple of demonstrations about sound. The first demonstration I want to show is of an animation of a tuning fork. In this animation, we see that the tuning fork tines are vibrating back and forth, and as they vibrate they make compressions and rarefactions. We hear it detected as sound waves when these compressions and rarefactions reach our eardrums. So I'm going to sketch a tuning fork and then show a simulation of a tuning fork to show that there's more than one vibrational mode of a tuning fork. So a tuning fork is this instrument that has a handle and two tines, and usually stamped on the tuning fork is a letter and a number. The letter stands for the note on the Western musical scale, and the number tells you the vibration in cycles per second, the frequency essentially of the tuning fork. I want to take you now to a simulation that shows a vibrating tuning fork. What I want to show you now is an animation of a tuning fork, different modes of vibration. And I'm going to let this guy talk about his modeling of a tuning fork. So he's got a tuning fork here that has been struck, and it vibrates in several different modes. It's the first mode that you hear. So we'll let this play now.
This is the first or fundamental mode, which corresponds to the frequency that we hear of the tuning fork. Obviously, the amplitude of this motion is exaggerated in this animation, so we can clearly see the mode shape and its motion. You'll notice the time motion is symmetric. This results in balanced forces, so we don't feel any strong force at the support. So our fingers do not dampen this motion. It's allowed to ring. This is the second mode of vibration. Each higher mode corresponds to a higher frequency. This is an example of an unbalanced mode. As the fork vibrates this way, we have large motion at the support. So obviously our fingers would dampen this motion out early on after hitting the fork. So we don't hear this frequency in the tuning fork motion. This is the third mode of vibration, which is also unbalanced. So we have large motion at the support. So obviously our fingers would dampen this motion as well. This is the fourth mode, also unbalanced. It's an out-of-plane vibration. And this is the fifth mode. This is the next mode which is balanced. We have very little motion at the support. So when you strike the tuning fork, this high frequency sound can be heard, although it does die out faster than the first mode vibration. Again, notice that the time motion is symmetrical, helping to create this balanced motion and no motion at the support. This is the sixth mode, which is actually very similar to the second mode of vibration, which is a torsional vibration. We just have more complex motion in the tines during the twisting. Again, it's unbalanced because of the motion at the bottom. With higher modes, the mode shapes become more complicated, more sinusoidal, but the motions are very similar to the lower modes. But again, they are occurring at a higher frequency and a more complicated shape. This is the eighth mode. Again, it's out of plane vibration with a more complicated mode shape and higher frequency. This is the ninth mode. Its frequency is more than 10 times the first mode, and we're getting a complicated piston-type motion of the tines caused by more vibration in the base of the fork. And again, this is a very unbalanced mode because of the extreme motion of the support.
So now what's happening is he's going to have the tuning fork being held and model the tuning fork in terms of being held by someone's fingers.
The first simulation was of unconstrained motion, so we had no support on the end. But when you hold the tuning fork, you're adding constraints and adding structure, which has material properties as well. That can affect the vibrations and the mode shapes and introduce more mode shapes and vibrations. This is the first mode of vibration, which is due mostly to the support. This is the second mode, also due to vibration of the support, allowing out-of-plane motion of the fork. This is the third mode, which corresponds to the first balanced vibrational mode of the fork. This is the same mode we saw in the unconstrained simulation before. You'll note that there's very little force or motion at the support, so our added structure has no effect or very little effect on this vibration. Again, this is the main vibration we hear when we strike a fork and hold it. This is the fourth mode, which is the first combined mode where we have vibration of both the structure and the fork, and this is a torsional vibration of each. This is the fifth mode, which is also a combined vibrational mode of our support and the fork. We're getting a lot of vibration of the fork at its base. Again, this type of mode cannot exist when we're holding the fork with our finger because there's too much relative motion and that motion would be damped out. This is the 12th mode. I've skipped several modes that represent other unbalanced and kind of unrealistic motions. This is the second balanced mode of vibration of the fork, which we saw with the unconstrained simulation. As you can see with this mode, there is a slight amount of motion of the bass due to the motion of these tines. So there would be some damping in our fingers holding the support. This is not a totally balanced mode. So you would expect this higher frequency sound to dampen out faster. And that is the case when you listen to the fork. You hear the higher pitch dampen out faster.
So the point of that simulation was to illustrate what's going on with the tuning fork and the different modes of vibration according to that model that was being used. You might think about the standing waves on a string that we demonstrated in class at one time where we had nodes and antinodes, and the model that you saw there is basically something that's similar to that when it's done with a two-dimensional or three-dimensional object like a tuning fork. Now I want to show a simulation in which we see that sound is a mechanical wave, which means that it requires a medium for transmission. So you recall that because sound is a wave, it's caused by a vibration. Maybe the vibration is of my voice, or maybe it's a ringing bell, or a buzzing timer, or some other vibration. So the vibration is made, and then the vibration is transmitted away from the source through some medium. Usually that medium is air if we're thinking about sound reaching our ears. Well, what if there is no medium? The vibrations may still occur, but there's not going to be any transmission of the vibrations. And that's what this next diagram is about. In this simulation we have a bell that's in a bell jar. I don't know why it's called a bell jar, except perhaps it looks like a bell. The bell is switched on. It's connected to a vacuum pump. The vacuum pump is switched on, and as the air is removed, you can hear the sound from the bell is reduced. As more and more of the medium is taken away, then there's less and less sound that you hear. Now this is not a perfect vacuum pump, so it's not going to get all the air out. So now air is going to be reintroduced into the chamber. You may be able to hear a slight vibration here before air is reintroduced. But as there's more and more of the medium reintroduced, the sound becomes louder and louder. If there's no medium, then there's not going to be any sound. One of the things you're going to need to know is that there's a certain range of frequencies to which humans are sensitive in vibrations. And we may do a demonstration of this in class, but I have a demonstration that I want to do here. In general, the frequencies that humans are sensitive to are in a range of between 20 hertz and 20 kilohertz, or 20,000 hertz. If there are vibrations that happen that are lower in frequency than 20 hertz, we say that they are infrasonic. And if there are frequencies that are higher than 20 kilohertz, we say that they are ultrasonic. There's another word that you'll hear which is kind of like these words, but it has a different meaning, and that's the word supersonic. When something is referred to as supersonic, what it means is that it is an object which is traveling faster than the speed of sound in that particular material or particular medium. Usually it's going to be the speed of sound in air. So if you talk about a supersonic jet or a supersonic bullet, then you're talking about an object that's traveling faster than the speed of sound, which happens to be about 343 meters per second in air that's at room temperature at standard pressure. Because sound is a wave, then we can use the relationship between wavelength and frequency and speed in order to solve problems involving sounds. And you'll see in your textbook that there is a table, 36.1, that shows you the speed of sound in various media. In air, at 0 degrees, the speed of sound is about 331 meters per second. At 100 degrees, it's 366 meters per second. This air is mainly a mixture of nitrogen and oxygen, about 80% nitrogen and 20% oxygen. Carbon dioxide, the speed of sound is slower, whereas in hydrogen the speed of sound is faster. In general, we're going to be dealing with the speed of sound in air at room temperature about 343 meters per second. In water, the speed is faster, 1490 meters per second. In solid materials, such as aluminum and copper and iron, you can see that the speed of sound is faster still. It turns out that there's a relationship between the stiffness of the material and the inertia of the particles of the material that determine what the speed of sound is going to be. That's not a relationship you need to know in general for the AP exam, but you ought to know that in general, speed of sound is fastest in solids, slowest in gases. When you work these problems, you're going to see that the speed of sound, V, is equal to the wavelength times the frequency. And a lot of these problems are going to involve using that equation. For the most part, if the number is not stated to you what the speed of sound is, then you can assume it's the speed of sound in air at room temperature, 343 meters per second. That's not a number you need to memorize, but it's a number that comes up quite a bit. It's one of my good friends. Example 36.3 says this. An observer sees the muzzle flash when a hunter fires a gun. If the observer hears the sound 3.24 seconds later, what's the distance between the hunter and the observer? The speed of sound on that day was 350 meters per second. Well, let's sketch a diagram and see if we can figure this problem out. Over here on the left-hand side, I have a hunter who's shooting at something up in a tree. Over here on the right-hand side, I have an observer with very big ears who is looking at this situation. And the observer sees the muzzle flash when the hunter fires the gun. The speed of light is 3 times 10 to the 8th meters per second. That light essentially travels instantly from the gun to the person who's listening. We're trying to figure out how far it is between the hunter and the observer. So when the hunter pulls the trigger, the flash is seen by the observer, and then the sound waves travel and take a time of 3.24 seconds until they reach the observer. Well, if the speed of sound is 350 meters per second, and that sound is not accelerating as it leaves the hunter and travels toward the observer, then I can use the distance formula. The speed, the average speed of the sound, is going to be the distance that the sound travels divided by the time that it takes to travel that distance and solve this particular problem. So let's do that. The speed of the sound in this case is equal to the distance the sound travels divided by the time it takes to travel that distance. Let's solve that equation for D. And now let's put in the numbers. The speed of the sound wave is 350 meters per second. The time is 3.24 seconds. And now feed those numbers into the calculator, and I get that the distance is 1,134 meters, just over a kilometer. By the way, if you're thinking about lightning and thunder, there's a rule that you can use to say how far away is the lightning flash. If you see the lightning flash, begin to count seconds. 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000. For every 5 seconds, the sound travels a distance of 1 mile, approximately. So if you see a flash of lightning and you hear the thunder 15 seconds later, you could say that lightning flash is about 3 miles away. So, for this lesson, that's it.